Now to the switch realization or the realization of the switches in a buck converter. Generally, there are two ways to realize the switches in a buck converter, and we call it either a synchronous buck or asynchronous buck. In a synchronous buck, essentially, we'll find that the two switches are realized using power transistor or power FETs. On the other hand, in asynchronous buck converter, we'll find that the switch 2 is realized using a diode, while switch 1 is realized using a power MOSFET, just like in a synchronous buck. And in this case, the way it works is that there is some kind of parasitic capacitance at the switching node. And as we mentioned before, the inductor current is basically positive. So it's flowing from left to right. And while this switch is on, as we mentioned, during phase 1, the inductor current increases until it reaches its maximum value. Then switch 1 is going to close. And what happened at that instant, the inductor is carrying its maximum amount of current, positive, and flowing from left to right. While the diode is still reverse biased. So what's going to happen is this inductor current is going to flow in the parasitic capacitance that's connected at the switching node. And this node will discharge from Vn all the way to ground. And in fact, it will go a little bit below ground. It will go below ground by minus V diode, whereas V diode is basically the forward voltage of this diode. And so this node goes to minus V diode, and at that instant this diode is going to carry the inductor current, and essentially the inductor current start to decrease. One thing to note in a asynchronous buck is that the voltage across the inductor, if we consider this is a positive terminal of the inductor, is going to be minus V diode during the second phase, or in this interval is going to be minus V diode minus V out, or basically minus V diode plus V out. Now, how to find the required inductance value in a buck converter. First of all, what are the givens for the design of a buck converter? We are given basically the input voltage. Say we are given that we need to design a buck converter with an input voltage equal to 48 volts and output voltage equal to 12 volts and a load resistance or an output current say equal to 10 ampere. These are the givens. So the first unknown obviously is what's going to be the duty cycle of the clocks that are driving switches S1 and S2. And that's simple to do. We already knew that the conversion ratio of the buck converter is equal to the duty cycle of the clock, which is equal to V out, or the ratio between V out over Vn. And so basically we have 12 volt divided by 48 volt, or basically 1 over 4 in this case. So that's the first unknown. However, we have also other 7 unknowns in addition to the required duty cycle. The first one, what are the sizes of the passives? So we have an LC filter. What is the value of this inductance? Also, what are the rated current, RMS current of this inductance? What's the saturation current, as we're going to discuss? Also, what is the required capacitance for the output decoupling? Also, as we know, any capacitor has RMS current rating and maximum voltage rating. In addition, we'll notice that there are some parasitics at the input line, inductances and ESR, equivalent series resistance, so we need to use an input decoupling capacitance. So similarly, we need to find what is the required input decoupling capacitance, what is RMS current rating, what is maximum voltage. And then for the switches, we need first to determine what is the required on resistance, and also they have ratings, what is the required maximum voltage, and what is the required maximum current they have to handle. And finally, what is the switching frequency of the clock that's driving switches S1 and S2. So in total, we have 8 unknowns. Finding the expression for the conversion ratio as the duty cycle, this solves the first or sets the equation that defines the first unknown, so we are good with the first unknown. We know how to calculate. Now let's see how to find the required inductance value in the LC filter. And to do that, we need to find the maximum and minimum current that flows into the inductor. We mentioned before that the inductor current will have a triangular waveform versus time. It increases during the first phase while S1 is on, and then it decreases in the second phase when S2 is on. So it has a maximum current value, I max, and it has a minimum current value, I min. So we need to find equations that describe the maximum current flowing in the inductor and the minimum current flowing in the inductor as a function of the inductance. And from that, we'll be able to get the design equations that define the required inductance to use in the buck converter. So the maximum current that's flowing in the inductor as shown here can be expressed as in terms of the DC component or average component of the inductor current, as well as the ripple component of the inductor current. We mentioned, as I said, the inductor current is triangular, increasing during the first phase while S1 is on, and decreasing during the second phase or while S2 is on. And as you can see, there is a peak-to-peak ripple of the inductor current, delta IL. And also, the inductor current, it's a periodic signal from Fourier series, is going to have a DC or average component, as shown here. And we call it I capital L capital. So we can express the maximum current flowing into the inductor in terms of the average component and the ripple component as IL, the average component, plus half of the ripple peak-to-peak inductor ripple current. And the minimum value can be expressed as IL minus half the peak-to-peak inductor current ripple. So now the problem boils down to we need to find an expression for the inductor average current component and the inductor peak-to-peak current ripple in order to be able to find an expression for the maximum current in the inductor and the minimum current in the inductor. But first, there is a small question. Why did we assume the average current to be exactly in the middle between the max and minimum? As you can see, the average is separated by an equal distance from the maximum current and the minimum current, delta IL over 2 and delta IL over 2. Why it's not like here as shown here? Why the average is not closer to the minimum value or closer to the maximum value? Well, it's really simple. The simple reason you can say the average current is basically the area I under the inductor current waveform over one cycle divided by the cycle time. So we know that the average current of the inductor we integrate over one cycle, the inductor current, and this basically will give us the DC or average component of the inductor current I capital L capital. And since these triangles are identical, the positive and negative are going to cancel each other, and essentially we'll find that the area is given by this rectangular box, and that's why the average has to be in the middle between the max and minimum. Another way to look at that is if we evaluate this expression for the inductor average current, as I mentioned, the integration over one cycle divided by the cycle time. And we say that integration, of course, as we know, is basically the area under the curve. So it's going to be the area under this inductor current waveform. And as you can see, it consists of two areas. The area on the left is a trapezoid, area 1. And the area on the right is also another trapezoid, A2. And this trapezoid area is given by basically the area of the base, so dt, times the I min h1 plus h2 over 2, as given by this expression. So the base is basically dt, while the h1 is equal to I min plus h2 is I max, and divide all that by 2. And then the area of the second trapezoid is basically the base, W, which is 1 minus D times T. And then again H1 is I max plus I min is H2 divided by 2. And so the inductor average value is basically 1 over 2 over t, the cycle time, times area 1 plus area 2. And if we evaluate this expression, add a1 to a2 and divide by t, you will find that the average inductor current IL is basically the minimum inductor current plus peak-to-peak inductor current ripple divided by 2. So essentially it's going to be I min, add to it half the inductor current peak-to-peak ripple value. So going back to what we are trying to get, as I mentioned, in order to find the value of the required inductance in the buck converter, we need to find an expression for the maximum current in the inductor, minimum current in the inductor. And then we said, well, we can express these in terms of the average component of the inductor current, as well as its peak-to-peak ripple component. So now what we're going to start with is we're going to try to find an expression for the inductor average current component. As we know, any periodic signal, the inductor current is a periodic signal, and it can be represented in using Fourier series as a DC component in addition to higher order harmonics, fundamental, third, fifth, and so on. And since the LC filter is basically a linear circuit, excluding the switches S1 and S2, I'm just considering the output side LC second order filter is a linear circuit, so we can apply KCL at each harmonic component alone. So we can apply it at DC, and then we can apply it at the fundamental alone, the third harmonic alone, and so on. So let's apply the KCL, Kirchhoff current law, at the output node for the DC component alone. As we know, at DC, the capacitor is open circuit because it's equal to 1 over SC or J omega C, and if as the frequency is 0, this will be infinite value, so essentially open circuit. And this means the DC component, or the average current flowing in the inductor, is going to be equal to the current flowing in the output resistor, or the load current. So essentially, the inductor average current component is equal to the load current, which is equal to the output voltage divided by the load resistance R. So that's the first part. We calculated the average component or the inductor average current component. The second part, we need to find an expression for the inductor peak-to-peak ripple current. And to do that, it's very simple. Since this is a triangle, the peak-to-peak ripple is the height of this triangle, delta L. And to find that, we can multiply the base of the triangle times its slope, or the slope of the this straight line of the inductor current during the first phase, or while S1 is on. And so basically, delta IL will be equal to the slope times the base dt. And then the slope of the straight line, this line, we already know that in the first phase, if we look here, in the first phase, the voltage across the inductor is equal to the input voltage minus the output voltage. And inductor voltage, as we know, is basically its value and its inductance times the first derivative of the inductor current. And so the slope of the inductor current during the first phase while S1 is on, di L by dt, will be equal to the difference between input and output divided by the inductance L. Okay, so we can use that value here. After that, we can simplify this expression. We can take Vn as a common factor in the numerator, and we end up V out divided by Vn times dt, and all that divided by L. We know that V out over Vn is the duty cycle. So if I continue on this side, so this is going to be equal to Vn multiplied by 1 minus the duty cycle, which is essentially the conversion ratio of the buck converter, which is equal to V out over Vn divided by the inductance L. Then we have D and T. We know that the cycle time is 1 over F, where F is the switching frequency. So this gives us the peak-to-peak inductor ripple current, delta IL, will be the input voltage times D times 1 minus D divided by F times L. Okay. So delta IL, the peak-to-peak value of the inductor current ripple, is going to be the input voltage times the duty cycle 1 minus D divided by F times L. And so we found delta IL, we found the average value of the inductor current as the output voltage divided by the load resistance, or essentially the current flowing in the load. And so from that we can find Imax and Imin, where Imax is the average component plus half the inductor peak-to-peak ripple current, and the minimum is IL minus delta IL over 2, as given in here. All we did is just divide the peak-to-peak ripple expression by 2, and the average component is essentially the load current. One point here to consider before moving ahead with the remaining or expressing Imax and Imin and getting the equation for the required inductance in a buck converter, I like to clarify how the peak-to-peak value of the inductor current ripple depends on the input voltage. obviously is proportional to the input voltage. So the higher the input voltage to the buck converter, the higher the ripple for the same load current, as you can see here. So this is for a small input, the peak-to-peak ripple is small, and then for higher input voltage it will have a much larger value. And in both cases the average value of the inductor current doesn't change because it's always equal to the load current. So for the same load current, increasing the input voltage is going to increase the peak-to-peak value. And the same thing, if we increase the frequency or the inductance used for the buck converter, we'll find for the same load current, we'll find that the peak-to-peak ripple is going to decrease. Now, what about how the peak-to-peak ripple depends on the duty cycle? Well, this is a quadratic function, x times 1 minus x. So we expect that it will increase to reach a maximum value, then it's going to decrease. As shown in this figure, this is the duty cycle of the buck converter. It changes between 0 and 1. And as you can see, the peak-to-peak ripple of the inductor increases until it reaches a maximum value at a duty cycle equal to 0.5. And after that, it starts to decrease. So the critical point that defines the maximum peak-to-peak ripple in the inductor is basically when the duty cycle is equal to 0.5. Now, continuing with finding an equation that defines the required inductance in the buck converter, we find an expression for the maximum current and the minimum current. Later on, we'll find that the maximum current defined essentially the ratings required for the inductor current and its saturation rating basically. But for now, this expression, the only thing we have is typically we prefer to express Imax and Imin in terms of the output voltage rather than the input voltage. And the reason is simple, because typically there is a sense resistor that's connected in series with the input in order to be able to sense the current that's flowing to the buck converter and be able to control its maximum value, or essentially control the maximum value of the inductor current via a feedback control loop. So there is a sense resistance, so we expect that the actual input, this node, the actual input to the buck converter will have a lower voltage value than the actual Vn. And so that we don't have far equations from what we're actually going to have. Essentially, we'd like to replace Vn times the duty cycle in Imax and Imin by Vout, because Vout is going to be controlled at a specific value using the control loop. Say it will be always at 12 volt within plus minus 1%. So it's better to express Imax and Imin in terms of Vout instead of Vn, given the sense resistance that will shift down the value of Vn a little bit. Now, let's get the equation that defines the required inductance for a buck converter. Now, assume that the load current that's flowing in the load resistance, we said is essentially I out, is equal to the average component of the inductor current. So as we reduce I out, say this is 1 ampere, then we reduce it to 0.5 ampere. As you can see, the average went down while the peak-to-peak ripple didn't change. And let's reduce it further from 0.5 ampere to say 100 milliamps. And at 100 milliamps, as you can see, the inductor current reaches 0 at the at integer multiples of the cycle time, 0t, 2t, 3t, and so on. Now let's reduce the load current even further from 100 milliampere to say 50 milliampere. So you see that now the inductor current has negative values. And during the first phase, S1 is on. During the second phase, S2 is on. And while S1 is on, negative current means that it's current flowing from right to left instead of left to right. And so essentially, the inductor is taking current from the output and sending it back to the input. And similarly, in the while S2 is on, The negative current means that the current is flowing right to left, and so essentially the inductor is taking current from the output and throwing it away to the ground or dumping it into the ground. So in both cases, it's essentially we want power to flow from the source to the load or from left to right. However, when the inductor average current is such that its minimum value has negative value, this causes the inductor to return the power is sending to the output during phase 1 and during phase 2, which lowers essentially the efficiency of the buck converter. So we want to avoid that. We don't want the inductor current or the minimum current of the inductor to have a negative value. The minimum value should be larger than 0. So that's number 1. Now, the inductor current will have a negative value in a synchronous implementation when S1 and S2 are implemented using power transistors. However, in asynchronous implementation, when S2 is implemented using a diode instead of a switch, we'll find that the diode will not permit negative current, right? Will not conduct while it's reverse biased. And so essentially, we'll find that the inductor current will increase while S1 is on, that's fine. And then it is going to decrease when S1 is off. It's going to decrease until the diode is going to pick up the inductor current. And since the diode doesn't allow negative current or the flow of the current in the inductor from right to left, so essentially it's going to become off or open circuit essentially. And so there will be an interval during which both S1 and S2 are off. S1 and S2, or S1 and the diode, will be off. In synchronous implementation, so this curve in gray, that's for synchronous implementation when S2 is implemented also using a power transistor, we'll find that the inductor current can have negative values because power transistor will allow current to flow in both directions. While if you use S2 in asynchronous implementation, as I just mentioned, the inductor current essentially will never be negative, and there will be an interval during which both S1 and S2 are 0. The problem is, so when the inductor current is always continuous, doesn't go to 0, we call that continuous conduction mode of a buck converter. So essentially, buck converter can operate in one of two modes: continuous conduction mode, and in this mode, the inductor current is going to be of continuous value. And the second mode in which a buck converter can operate is called discontinuous conduction mode, where the inductor current reaches 0 before the beginning of the following cycle. So essentially, as the name suggests, the current in the inductor is basically discontinuous instead of being continuous. And the issue in the discontinuous conduction mode that happens as shown in this graph when the inductor current is discontinuous is that the output voltage, instead of being a function of the duty cycle and the input voltage only, the output voltage will also be function of duty, Vn, as well as of the load current. And so imagine that you set the duty cycle at 0.4 or 40%. When the buck converter is in continuous conduction mode, and the current in the inductor is continuous, it will give the output is going to be 0.4 times the input voltage. On the other hand, if the inductor current is discontinuous and the buck is operating in discontinuous conduction mode, you will find that for 1 ampere current, the output voltage will be, say, 0.45. The input voltage increases from 0.4 to 0.45. And when the inductor current, say, is 100 milliamp, or sorry, when the load current is 100 milliampere, the output voltage is going to increase to, say, 0.58 the input voltage, although we are using the same duty cycle. And then when the load current is say 10 milliamp, the output will reach say 0.95 Vn. So as you can see in the discontinuous conduction mode, the output voltage became a function of the load current, and this complicates the control loop, make it nonlinear, and that's something we need to avoid. We prefer the output voltage to be only function of the duty cycle, which is a controlling variable of the loop, and the input voltage, which is supposed to be constant ideal. So my point here is, in both cases, synchronous will lead to negative current, which lowers the efficiency. Asynchronous will lead to discontinuous conduction mode, which make control difficult. So in both cases, we said that the minimum current of the inductor should be larger than 0 to avoid discontinuous conduction mode and circulating currents in a synchronous implementation. And from this condition, we'll be able to set the required inductance value, because if you remember, we found that the peak-to-peak current of the inductor, this delta IL, is equal to what? Vn, or Vn times the duty, 1 minus divided by Fl. So if we increase the value of L, we'll be able to reduce the peak-to-peak ripple. And therefore, the average current, which is essentially the load current, is equal to the peak-to-peak ripple, inductor current ripple, divided by 2. This distance is essentially delta IL over 2. And so if we increase the inductance value, we reduce delta IL, and so we reduce delta IL over 2, or we allow smaller values for the output current to have continuous conduction mode and avoid any negative or circulating currents, essentially. Okay. So Imin is given by this expression as I showed a few slides ago. And if we simplify this equation, we'll find that the required minimum inductance should be larger than this expression. We'll find that in the numerator we have V out, at the numerator we have I out. The ratio between V out and I out is basically the load resistance R. And then if we look at this expression, we find that, well, the minimum inductance value, the largest value for Lmin, will happen when the duty cycle approaches 0, is almost 0, right? When D is almost 0, the right side of this equation or inequality essentially is going to has its largest value. So the worst case for Lmin should be larger than R over 2F. Now we can move 2F to the other side and multiply by pi. So 2F Lmin should be larger than pi times R. Or basically, the impedance of the minimum inductance must be larger than pi R in order to avoid discontinuous conduction mode and in asynchronous implementation and circulating currents in synchronous part, which is given by this equation. Okay, so this is basically what sets the this is basically the equations that help us define or set the inductance values that we should use for our design, buck design. And again, the minimum required inductance for our buck design can be lowered by increasing the switching frequency. So if we switch at 100 kilohertz, we can expect that, say, and the inductance is the required minimum inductance to avoid discontinuous conduction mode is equal, say, to 100 microhenry. If we select the switching frequency to be 1 megahertz, 10 times larger, according to this equation, we find that the minimum required inductance decreases from 100 microhenry to 10 microhenry, 10 times. And why we need to reduce the value of inductance? Why we want to reduce the value of inductance? Well, inductance is one of the expensive elements in a buck converter, or generally in most power converters. So two things, as you can see, here we have three inductances, 27 nanohenry, 330 nanohenry, and 10 microhenry. And if we look at the price of the 27 nanohenry is $1.1, while for the 10 microhenry is 10 times, more than 10 times larger. Okay, that's why we wanna use the smallest inductance possible, and we should increase the frequency. And that's typically the trend in research, is trying to operate at higher and higher frequencies to minimize the size of the passives and the cost of the passive. The other thing you notice is this is 2.1 millimeter, while the width of this 10 microhenry inductor is 10 times larger. Okay, so always remember, we want to reduce the value of the passive, whether it's inductance or capacitance.